All right, I almost launched into this in the last video, but I think it fits better as its own. So I've got the process of going from toluene to trinitrotoluene, or TNT, on the board now. These are all nitrations. Remember, nitric acid and sulfuric acid are going to react to produce NO2+. And then the aromatic ring is going to be a nucleophile that attacks NO2+, and you wind up with NO2 substituting for hydrogen. In the first reaction, the methyl, which is a weak electron donor, right? So methyl is going to direct ortho or para. I'm going to show it going para. It's going to go para more than ortho because of sterics. But at this point, you might have a little bit of ortho as well. All right, then if we nitrate para-nitrotoluene, we add a second nitro group, ortho to the methyl. Again, the methyl's a weak donor. Nitro is an electron withdrawing group. All right, the donor is going to rule where this goes. Both groups point to the same place, but really what's controlling this reaction is the methyl. And then if we nitrate again, the next nitro goes ortho to the methyl again. And then the reaction stops because you've occupied the ortho and para positions for the methyl, and now there's nowhere else. The meta position's deactivated for methyl. Well, that's what we're getting to. That's actually what the point of this video is. This first reaction is fast. Toluene nitrates really nicely. It's easy. It's a really easy reaction to run. You do this at 0 degrees C. It would take about 20 minutes. You'd be done. I've never done this second one. The second one goes at 80 degrees C for 24 hours. Right? This one's hard to do. So the second reaction is slow. The effect of the nitro group is to slow the reaction. Right. I'll put this in black. The nitro group slows the electrophilic aromatic substitution down. You can tell because the first nitro goes on super easy at 0 degrees, really quick, 20 minutes. You never see any dinitrated product here. To do the second one, you have to heat it up to 80 degrees, you have to let it go for a full day. And then this third reaction is like, I think it's 200 degrees or something. With some pressure. Under pressure to get the third one on. So the second, if one nitro slows the reaction down, the second nitro slows it down even further. And so now think what you're doing. You're making TNT. TNT is the product of this reaction. TNT explodes. And you're making it at a high temperature and pressure. So TNT is actually, explosives in general are really hard to make because the product you're making explodes. Right, so you think about it. You're standing there at the bench. You got this stuff in a flask. Like you don't want explosive in your ground glass or in your glass flask. And so TNT is made in special factories that they don't put a lot of money into to build because they sort of assume it's going to explode. Explosives are terrible. Well, actually, I shouldn't say that. Explosives have built much of the world. Right, if you go in to do construction. If you've ever dug in a garden and you hit a rock or something, so imagine you got to put a foundation in, right? So explosives are used to clear ground for construction, bridges, tunnels, all that sort of stuff. They're also obviously used to kill. It's a chemical miracle almost that we humans can make explosives as well as we can. And we've put a lot of money into it because we like killing each other. It's supposed to be apolitical, sorry. Anyway, the point here is the NO2 group slows the reaction down. And from this, we get this rule. Electron donating groups So here's our rule. An electron donating group activates a benzene to electrophilic aromatic substitution. These are both relative to H. Right? So if I have a methyl group, like toluene would react faster than benzene. Let's try that. Right? So if I put toluene and benzene in solution with nitric acid and sulfuric acid, I'll get toluene nitrated, and benzene won't react. Okay, so the toluene is going to react faster than benzene because the toluene is a weak electron donor. So relative to H, the toluene is a more reactive molecule. If, on the other hand, well, I'm put this over here. If I have nitrobenzene and sulfuric acid, that's all I get. Huh, that's bad. Let me do this differently. Sorry. I wrote this down on paper and it didn't look weird. Okay, so ignore what I said first. Right? If I have a ketone on a benzene, that carbon's positive. The ketone's an electron withdrawing group, and so this ring is deactivated. Excuse me. And what I mean by that is it doesn't react as well as benzene that has an H here, right? So if I take these two and I subject it to nitrating conditions, I'll only nitrate the benzene. I won't nitrate the electron core. And you can also see here, right? So an electron donating group activates aromatic rings to electrophilic aromatic substitution, and they're ortho paradirectors. Electron withdrawing groups deactivate aromatic rings to electrophilic aromatic substitutions, and they're metadirectors. Okay? There is a big exception to this. This is a general chart that you should know. You should be able to explain it, but you should know it whether you can explain it or not. And then in the next video, I'll walk through this exception. The exception to this are halides. All right, so if the substituent is bromine, chlorine, or iodine, it doesn't fit this chart.